Hello everyone. Myself Vikram Prem Kumar from NITK second year EC department, and today I'm going to be explaining a very important algorithm used in AI accelerators, and which serves as a speed up algorithm for convolutions, which is the Winograd Minimal Filtering Algorithm, which accelerates convolution neural network used for CNNs. So let's dive into it right on. So before we get into the what of the algorithm, let's understand why it matters, why speeding up convolution matters. It said that 90% of the computation bottleneck in CNNs is the processing time. What are we processing? The multiplications. The millions of multiplications which takes place while processing an image, for example, is what causes 90% of the computation bottleneck. And we've got only small filters. So now we use smaller kernels. So the 3 cross 3 kernels are the ones which we use most of the time in order to compute them. So for example, if you've got a 28 cross 28 image of pixels, we've got 784 pixel values. We run a 3 cross 3 kernel. We slide it across that image and we compute individual uh, element-wise multiplication. Now, if you go on computing every individual values, it is going to be a huge multiplication, and multiplication cost is huge. That is what causes the huge computation bottleneck. So now but why do we need to do this multiplication is but because most of the AI models run using these algorithms. So improving the efficiency and improving the speed is the most important aspect in AI nowadays. So the challenge with conventional methods is that if you do direct convolution, which I've told, if you've got a 784 pixel values, if you do direct multiplication with those kernels, there's going to be a huge number of multiplication values which you're going to obtain. And those multiplication cost itself is going to take a lot of time. So direct convolution is that the complexity with excessive multiplication operations, it slows down the processing time dynamically and dramatically. So even the fast Fourier transform based approach, it is efficient for large filters, but in recently, I mean, most of the the kernels which we use are small filters, which is 3 cross 3 sized. And we can't go into these large filters because it introduces unnecessary overhead. And also the optimization gap because algorithms are specifically designed for smaller filter sizes. So this is where Winograd's minimal filtering algorithm comes in, and let's dive into the what of the algorithm. So it was born from a Tomb-Cook multiplication generalized by Shmuel Winograd in the 80s. So what it basically does is instead of trying to compute every multiplication directly, performing convolution basically, we try to reduce the number of multiplications so as to improve computational efficiency. As we can see, it has a 4x times multiplication reduction and 90% time savings. So how it works? Basically, we use a specific formula. We use the input vector, which we are giving in, and then we've got a predefined set of matrices, the A, G, and B, and we perform element-wise multiplication, and then we perform inverse transform to get the output. So soon I'll be showing a visualization of how it works. So first, let me explain what the formula is. So here you can see the formula, which is right here. Y is equal to A transpose times B transpose TB. Now it might look complicated. I've explained that clearly. So A transpose is the transformation matrix which we perform on the value which we get from the inner bracket values. And G is the filter transformation matrix. That is the kernel transformation and the PT is the input transformation. So now it might sound complicated, but soon enough I'll show how these are derived. And D is the input tile or patch. G is the filter kernel. So the Hadamard multiplication is basically instead of performing a matrix multiplication, we perform element-wise multiplication. For example, the element at position 1 cross 1 is multiplied with the element at position 1 cross 1 itself. And Y is the output result. So this is the how we obtain these predefined A, G, B matrices. So let's take a sample input vector. So deriving them, we start with 1D convolution. So let's just start with a sample polynomial, which is a four variables are there. We've got D0, D1, D2, D3, and G is the filter kernel, which so these are like starting. This is just introduction. So G naught, G0, G, which is G naught, G1, and G2. And then if we compute them as polynomials, we've got D naught plus D1x plus D2x squared plus D3x cubed. And similarly for the G of x. Now, if you compute the y of x, which is equal to d of x times g of x, if you do direct multiplication, it's going to take a lot of multiplication, uh, which is what we are trying to reduce over here. So at the end, we are trying to obtain f2, comma 3. Now, what is f2, comma 3? f2, comma 3 is basically two output value with the 3 cross 3 input kernel. Right now, it's just a 1D matrix. Soon enough, I'll show the actual multiplication which will take place. Now we compute these values over here. We can see the values are computed at these specific points, 0, 1, -1, and infinity. Now, why those specific points is to simplify computation and make those transforms simple and to have as minimal the amount of multiplication as possible. So after evaluating g of x at these specific points, this is the matrix. So this matrix is basically taking the coefficients at each location. So G0 has 1, 0, 0 coefficients. So G1 has 1, 1, 1 coefficients. But if you look at over here, it has been scaled by half. Now, why it has been scaled by half? That is it's the convention used in most modern convolution methods, which is in the Winograd algorithm. It's a convention to scale these locations. So it's by default, that is the algorithm, what we do. So we scale it at those locations. So for 1, 1, 1, 1, -1, -1, and here you've got 0, 0, 1. We scale them at these two rows. So now this is the G matrix. Similarly, we can evaluate B transpose by computing D of x at these specific locations, and then computing the matrix values just like this by listing down their coefficients and taking the transpose of that, and then we'll get that the output value will be the B transpose, which will. So now here we've got y of x, which is equal to y naught plus. This is the output which you're getting, the two values, two output terms as indicated over here. How we get those values is basically by again computing them at these specific locations. We get y naught plus y1 of x. So that will be the first x at x equals 0, we get m naught equals y naught, m1, m2, m3. So now by rearranging and reclassifying, scaling, adding up, we will get y naught plus y naught and y1 as these terms. Now these are not directly obtained from this. We scale them and we add them. Uh, so this is the convention similar to this. This is the conventional formula which we use generally in Winograd's algorithm. So now if we take after computing this, if we take their coefficients, we'll get the A transpose, which is the coefficient values of these. And that is how we obtain the three matrix values. If you want in depth, we can make another video about just explain. So this is the visualization of the Winograd convolution. So here you can see the matrices, the input transformation matrices. There I've shown you using polynomials. These are the actual transformation matrices, the 4 cross 4 input vector, the 3 cross 4, the 4 cross 3 uh, kernel. So this is actually the kernel which we've obtained from over there, which we use for transformation. The A transpose output transform, and the B which you obtain after computing the B transpose of transpose. See, these are the basic matrices which we use for computation. And here we can see our input vector, the input matrix. And this is our kernel, which we are going to slide upon these matrix. We can change these values too. So for example, let's randomize these values. So let's take random values. and we've got random kernel size. So here you can see the full complete data flow. We start with the input vector, input matrix, and we perform the following computation, and we get this input the vector, and then we perform the Hadamard element wise with the filter to obtain these values, and then these values are further computed. We perform 16 multiplications, and then we get the output for this vector. For this value, we get output over here, and this is the formula as told, which is already shown. And let's go to the next stage. And from we are computing the next value, which is using the B transpose, which you obtain from from these matrices over here. This B transpose, we are going to multiply input D matrix and for compute again with B according to this formula. We are going to get the output value U. So this is the flow. As you can see over here, this is the final value which you get. And then we go to the next step. Next step is the filter transform. So we can see the four steps over here. The input transform, filter transform. Hadamard is basically, as explained, the element-wise multiplication. This is the output transform. In the second step, we can see the calculation of matrix V using the G input matrix, 4 cross the matrix, multiplying with the kernel and with its transpose to get P G dot product, and then we obtain finally V. As told before, the filter G is fixed. It is computed before processing any of the tiles. And then this is the final step, which is performing the Hadamard, the the step before the final step, which is performing element-wise multiplication. So here we can see this some of the multiplications are skipped because they are not used in the final in obtaining the final output value because they are essentially multiplied with zero. So they are not used, and so hence they are discarded. So we can see the element wise as I run my cursor over each of the values, we can see the element wise multiplication over here, over this one, this, or this, or this. So these are the values which you obtain in the finally. And the last step is to compute A transpose times the M which you obtained in the previous step with the A value to get the final Y, which is our output final value, which over here, if you can see by using Winograd, we can see the result too. Standard convolution uses 36 multiplications, huge multiplication cost, but Winograd uses only 16 of them. Hence, hence there's a 2.25 times speed up for this sized matrix, but on an average, I'll show that I'll show in the comparison slide how much faster it has been. Currently, let's complete the visualization. So this is the output matrix which you obtain, the 2 cross 2 output matrix. In the previous polynomial example, I showed you the 1D matrix which you obtain using the polynomials. Here we've obtained the actual matrix which you'll obtain during convolutions. And these are the two values. So now let's go to the comparison part. So here we can see using direct 2D convolution, we've got 36 multiplication with 32 additions. So multiplication cost is higher than addition cost. So that's why we can see even though additions are higher in this, there are fewer multiplications and hence it's computationally more efficient and faster. And here we can see how much faster it is compared to direct convolution. So as it increases, the efficiency and the speed up process also increases. But there is a limit to this too, as the kernel size is the limitation in Winograd algorithm, which we'll see in the further slides, that as we increase the kernel size, there are some disadvantages we encounter, which I'll be explaining soon. So after the visualization, let's come back to the practical implementations and the performance gains. So this slide will essentially explain us where it can be used and where it isn't currently used. So in NVIDIA optimization, CNN, convolution neural networks, achieve a 1.85 times speed up over CODN and Winograd implementations on modern GPUs. So modern GPUs still continue to use OpenCNN, but for smaller batches, there is an efficient performance. Basically, the smaller low power edge devices which use kernels of size 1 to 64, they are perfect. The Winograd algorithm is perfect for those applications, and it's also memory efficient because of its smaller memory footprint compared to fast Fourier transform convolution methods. So let's come to the hardware efficiency and parallelism part. The parallel processing power of the Winograd algorithm is huge because it enables parallel hardware implementation and hence requiring just 30% fewer multipliers as shown by this pie chart. It saves 30% multipliers, basically the multiplication cost, huge energy reduction, and it cuts operation cost. And because of this efficiency, this algorithm is very ideal for low power edge devices, IoT applications, and resource constrained embedded systems where every watt matters. So here in recent innovations, we talk about deep reuse and energy savings. Using the Drew method, which combines Winograd with deep reuse of intermediate computations. So essentially, instead of computing every multiplication uh, straightforward, we try to reduce the multiplication by taking in the intermediate values and computing them along with the further multiplication, and hence basically pipelining these values and reducing computation cost. And this will essentially obtain 8.27 times speed up, which have been achieved on edge devices like the Raspberry Pi and the NVIDIA Jetson platforms. It also has a 60% energy cut, reducing operations to 10% of the original, dramatically lowering power consumption. So let's come to the limitations and the considerations. The numerical stability. Uh, when we use the larger kernel sizes, the G essentially, basically, our accuracy can dramatically reduce because of the accumulated floating point errors. These values, so these computations are primarily used for integer point. And the second constraint is the filter size because these algorithms can be used only for smaller kernels, and the complexity for integrating with the existing deep learning frameworks. So we conclude with the Winograd's role in future of CNNs. We can't take away any aspect that this is a game-changing algorithm. It is a mathematical breakthrough. Which has transformed convolutional neural networks and its efficiency. In order to obtain low-power device integrated with efficient AIs, these type of algorithms are the need of the hour. And the growing impact of such algorithms and research also continues to expand on the accessibility and performance of such algorithms and real-time AI future. This is the key to unlocking practical real-time artificial intelligence in resource-constrained environments. So obviously, in the future, we would like to obtain AI-powered devices in any type of environments where the energy consumption is quite high. So in future, so we need to reduce it as low as possible. And if we need to have AI devices at the to be powered at the palm of our hand, we need to make it run using very low power. And this is where the such algorithms come in handy. And that will be it. Thank you. And let's meet in another video. Thank you.